Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
This is episode 5, season 3, broadcasting from the campus of the University of North Dakota here in Grand Forks. We do have a live chat that's running, so if you have any questions or comments that you'd like to make throughout the podcast, please feel free to use that feature. And before I introduce our guest today, a disclaimer as always.
As always.
Robert, do you want to handle it this time?
Okay. The opinions or views expressed in this podcast are those of myself, Wayne, and our guests. They are not representative of the views of North Dakota, the University of North Dakota, the department. You know, pretty much it's us.
Or President Trump.
Our President Trump, yeah.
Maybe. So our special guest today is Rebecca and Jesse Rhoades, who's from the Department of Education, Health, and Behavioral Studies here at the University of North Dakota. So I'll let them introduce themselves in more detail. So please take it away.
Hi, my name is Jesse Rhoades. I'm a professor in the Department of Kinesiology, and I teach biomechanics.
My name is Rebecca Rhoades, and you can call me Becky. Please call me
Okay.
Becky. I am a researcher at the University of North Dakota, and I also am an instructor for the kinesiology.
Nice.
Okay.
So Becky and Jesse, please, thank you for joining us.
Indeed.
Now, the reason why we had you on this podcast, which we mainly deal with, like space exploration, astronomy, those kind of things, is because I saw an article that you were involved in, and it's related to what's happening, hopefully in the not too distant future, regarding humans going back to the moon. So do you want to maybe elucidate a little bit on what your involvement is with that?
Well, so I'm a biomechanist, and I deal in kinesiology, which kinesiology typically is, kind of sports, right? But if you think about the study of kinesiology, it's the study of human movement, right? So what I've done is I've applied that study of human movement to space studies through my collaborations with Pablo de Leon and Keith Chrisman. And so what we are looking at, one of the key things that we kind of look at in biomechanics is human gait. That's just human walking or running, right? And the unique thing about going back to the moon or Mars is we're not going to be floating in a space station or floating in a spaceship anymore. We're actually going to be walking around, right? And so by walking around, we're going to be walking around in different gravitational constants. So we're going to have different environmental constraints on our bodies. And we evolved here for a very long time. And so going and spending a long period of time on the moon or Mars could have some interesting effects on our bodies. And so that's what I'm really interested in, is figuring out, what are those effects and how can we mediate any of the issues that may come up? And one of the big problems is that, with the Apollo missions, we were there for a few days, right? And now we're talking about months on end. So these issues that didn't come up 50 years ago with the Apollo missions are probably going to become pretty apparent when we go for Artemis.
Yeah.
Right.
Now, back in the Apollo program, so each of the spacesuits that the astronauts wore custom fit to the individual, as far as my understanding is. And we kind of got away from that during the space shuttle program, where spacesuits, came in certain sizes, and you
Right.
kind of, I guess you'd wear the one that best fit you, given what you have the option of. Do you see a time where when we go back to the moon again, or then on to Mars, or even in the far future somewhere else in the solar system, let's say that everything really needs to be custom made?
No, we actually had a student, Will Green. He just graduated with a PhD from UND, and his doctoral dissertation was on a very similar subject to that. And you're right, with the space station, we've kind of had, I'm not a spacesuit expert, so I sat on his committee, so that's how I can kind of go over this. That on the space station, we had 3 sizes, right? Where he looked at, what if we started modeling them for a person? So you take 3D scans and you actually tailor them directly for the individual. And What they found was obviously they can move better if you tailor
Right.
them for them, but it's very expensive, right?
Yes.
Right.
But the one thing that Dr. De Leon has been doing is working with 3D printed. And so he has that 3D printed spacesuit that he just got a patent on. And so if we can come up with a way to actually print these, then it becomes very, very cheap, right? Or at least less expensive than it is right now. And so they're probably going to go towards custom, but it's probably not going to be all out what we had in Apollo, where everything was fitted down to the last centimeter for every single one of the astronauts. I can't see us going back to that just for the amount of money that it costs. And the other interesting part is we now have commercial partners, right? So most of the spacesuits are not going to be, built by NASA. They're going to be built by commercial partners, and commercial partners are going to want to cut down on expense. So there's going to be a middle ground. There has to be a middle ground there.
Okay.
So one of the main targets, of course, with the Artemis project is go and explore the South Pole region of the moon, rather than going into an area like a really flat area, if you think of Apollo 11 and Sea of Tranquility. So that must give rise to lots of challenges, because if you're into an area like the South Pole, it's heavily cratered as far as we know. So chances are that if you're walking on the surface of the moon, and it is 1/6 gravity, but still your range of motion that the foot will undergo is going to be the same here on Earth, where you're walking down into little craters like craterlets or whatever, down the slopes of different hills and these kind of things. In fact, you'd wonder whether or not, even on Earth, if you're walking through a really messed up terrain in some sense, it's hard on the feet. If you're wearing a typical, like a sneaker or a shoe or something like this. So is there like a considerations that one has to think about and that type of terrain then versus like would happen like in Apollo 11?
Yeah, so that is mainly what we're looking at. When we go to the South Pole regions, you're talking about not just the bumpiness or the unevenness of the terrain, but we're talking cold. It's cold there. It's very, very cold there. So the spacesuits, they're already looking at ways in order to protect the astronauts and to keep them warm. Part of the thing that they've come up with so far is a rigid plate in the bottom of the boot that helps to protect the astronaut from the cold weather outside, and it warms them inside the suit. The thing is that it is rigid. There's no flexibility in it whatsoever. So not only are the astronauts going to be walking over this really bumpy and rocky terrain, but they're not going to be able to flex their foot at all. The boot is going to be stiff. And so that's what we've been looking at is, this first paper that we wrote was, does it even matter that the foot doesn't bend in the boot? And we're finding out that it really does. The astronauts could get hurt. They could get chronic injuries. So how are we going to fix that?
Right.
I actually have oh, go ahead.
I was just going to say, yeah, I was more concerned, if you're going over uneven terrain, it's usually a matter of your ankle area having to flex and rotate and bend. So if it stiffens up there, that would seem to be a real problem.
And with the Artemis boots, they have done quite a bit of work with the range of motion at the ankle joint.
Okay.
And so the boots are going to be able to invert and evert, and they're going to be able to plantar and dorsiflex at the ankle to some extent. There's always going to be rigidness with a suit, right?
Right.
Obviously, that's a concern. With the area at the South Pole, it is the terrain is very cratered. But the main thing that we're really worried about at this point is the cold, because you have permanently shaded regions that have not had sunlight in maybe 4.5 billion years, right? So
Right.
you have temperatures that are 50 Kelvin, so negative 369 degrees. I know it gets cold in North Dakota, but even we are not used to that type of cold.
Yeah.
Right.
And so material science is becoming a major issue there. So,
Okay.
one of our projects that we're actually working on right now, we have a NASA grant with Chanduska, and they have an advanced manufacturing program at Chanduska. And we are working on a outsole to lunar boots. And the whole purpose of the outsole is to exteriorize some of that movement. So if the foot can't make the movement, maybe the boot can make the movement, right? So we have spring levers and those types of things that are actually on the outside of the boot, and they're 3D printed. So they could print these in situ when they're actually on the moon. And so we're actually going through and testing those to see how good they are. But then we're thinking, hey, are these materials going to hold up, right? So we're printing out of nylon, out of Kevlar for these types of things. And even we're doing some metal as well. But the big consideration is this thing going to explode when it tries to bend in negative 300 degree weather?
Yeah. And what's nice about the outsoles is that it doesn't matter, or hopefully it wouldn't matter what spacesuit is chosen for the Artemis missions. It should be fairly universal. It just clips onto the boot and you go about your day.
I was about to say, so it's like the old skate keys with you just flip your
Yeah.
foot in. Okay.
Yeah.
Yep.
And that's the other thing that, with our outsole, one of the key things we put in our grant was that it has to be able to be actuated without hands, right?
Mhm.
Because with the spacesuit, bending over and tying your shoes does not happen.
Right.
Was there any problems, do you know, back in the Apollo days of heating the feet to keep them warm enough?
That is not in my area.
Yeah.
I know that at the equatorial region where they were, the temperatures were much more mild, right? So
Right.
we aren't looking at the cooling effects that we are going to have at the South Pole. So it wasn't as much of a concern, but again, that's out of my area.
Yeah, I know that the astronauts have complained a lot, even on the ISS, about their fingertips being cold a lot. So those kind of, extreme kind of limbs sticking out, must be a challenge. I was wondering about the design of new boots. Is there like electronic heaters that, like that kind of method that would be used to keep them?
I actually have a PowerPoint presentation.
Okay,
If I
cool.
can show
Okay.
slides.
So we
Certainly.
never planned this.
Okay, so I'm gonna share my screen.
Okay.
Can you see it?
We can.
Okay,
There we
so
go.
what we're looking at right now is the South Pole, and you see all of the little blue parts, the little blue specks. Those are where they think there's going to be water, and that's the whole reason to go to the South Pole is for water, right?
Right.
Hopefully I can get this to go. Okay, so yeah, I had a few of these. I don't need to show those yet because I was talking about boots. This is kind of what we're looking at with the boots. Over here is our Apollo boot. And the Apollo boot was really simple. It was just like a galosh. Pablo always talks about it just kind of being an over boot, right? And this fit over their flight boot. So they had a flight boot that they used in the command module. When they went out onto the lunar surface, they used these galoshes, right? Not a lot in there. If we look at these two, not that, go back. If you look at these two over here, like I said, we're actually relying on a lot of commercial vendors. So this is actually from a paper that was shown at ICES. It's an environmental systems conference that's held every year, and these are two companies that were actually vying to get the contract for the boots. And we see here an outsole that's very similar to the Apollo days, where it's just going to fit over. It's kind of a galosh. And then over here with the second vendor, we see kind of a boot where they're doing some other things with it, where it's a little bit more open design. But the key thing is this down here in figure 8. This is the thermal insert. So that's what the difference between the Artemis and the Apollo boots are, is this rigid thermal plate they're going to be putting in here. And the whole idea of active heating, we've actually discussed this. So I'm going to stop sharing my screen really quick.
Okay.
The whole idea of active heating. So it's an interesting idea, right? So we've talked about that when we were talking about cold, right? And so, yeah, you can have active heating in the boot, but then where does your power come from? How do you make sure that it maintains charge when you're out? What happens if you have electrical problems inside the boot? There's a whole bunch of stuff that comes along with having that active heating outsole, right? Or the insole. And so that they do discuss it. It's just one of those things that it's, spacesuits are so technically complex as it is, to add in another layer of complexity is kind of inviting issues to kind of rear their head.
Right. Because, the more complicated you make something, the more points of failure there are. And
Yeah, exactly.
Yeah.
So the design of the boot, if you don't have this active heating, then would rely on the heat that's emitted from the foot itself, and it's just a matter of keeping that heat trapped around the surface of the foot rather than letting it bleed off into space.
But that then leads to bulk, which inhibits movement.
But you can't have a frozen foot, so there's
But
got
you
to be
can't
a
have a frozen
trade-off,
foot.
right?
What is interesting is we actually we attended a conference this last summer where they were talking about this, and they were actually talking about the thermal insert in a boot in a vacuum chamber, and they were talking about its heat dissipation over time. And how cold did it get?
Oh God, it was cold.
They were talking about it being a very big success, but it still got very, very cold in that boot. And so, passive heating from the body is probably one of the better things. Now, they do a cooling garment with inside the spacesuit. So they do some of that work, but the whole idea of heating an area of the body like that far away is an issue.
Yeah.
The thermal plate is kind of the leading theory at this point, and that's kind of where our work comes in.
Yeah.
That we're kind of trying to show that maybe the thermal plate needs to have some changes done to it.
And it doesn't help any that your extremities are automatically the first things that get cold when it's cold outside anyway, and so it and
your body has regulators in it that say, hey, this is getting cold, shut down blood to the extremities.
Yeah.
And so, but I did have a question there. It looked like they're planning on putting this thermal plate on the bottom of the foot. Wouldn't it make more sense to put it on the top?
Probably. I would imagine that it has something to do with the fact that the surface and it being a barrier between the foot and the surface.
Yeah, it has something to do with the contact. Yeah. Again, I'm not an engineer, so it has to do with the foot being in contact with the regolith. And
it's the old thing of you put your blanket between you and the ground, not cover yourself with it because the ground is a bigger heat sink. Okay,
absolutely.
That makes sense. All right.
And even like walking, so you can imagine that astronauts will be on the moon at a given period, for up to 12 hours or 16 hours if they wanted to. That's a long time to be scuffling around on the surface in boots that you feel like you have snowshoes on or something, right?
Right.
That's going to automatically make the feet really tired. And maybe, you're trying to utilize as much time as you can while you're on the moon.
Right.
And you don't want to have to take a day off because your feet are so sore you just can't do your duty.
Exactly.
And I actually have a PowerPoint slide for that.
Wasn't planned either.
It's all right.
No, that's great.
So, so if I'm going to go back really quick.
Okay.
So if you look at how they were on the moon, I've got, these are just random ones. You can actually see that when they're moving around, they've got, it's obvious that they have a flight phase, but they are making contact with the ground quite a bit. Here's actually a pretty good one as well. And I think I like this one because back here you can kind of see that he has a normal heel and toe off. So we're getting some of the normal stuff. And we were just looking at those, but we have in our lab, we are able to do lunar offloading, right? So we're able to actually look in the biped lab at what a lunar gate would actually look like, right? So I can bring a participant in, we put them in a harness, we have a device that will actually offload them to lunar gravity, and then we can actually look at what they're doing, right? So we have a motion capture system that we can capture everything we need, right? And so when you look at the foot, so we were just talking about feet getting tired, this area on the bottom of your foot is called the plantar fascia. Now that is made up of collagenous material. It's made up of tendon, ligament. It's made up of contractile material, so it's made up of muscles. This all plays into when you have a toe off, which we just saw in our lunar walking from the Apollo missions. At toe off, we have this mechanism called the windlass mechanism that kicks in, and that happens right up here at our toe, right? So when we go to toe off, all of our ground reaction forces are on our big toe and little toes. It's called the hallux, and we dorsiflex or bend our toes up at the MTP joint. That's that joint right between your foot and the big toe. And when you do that, it actually creates a rigid platform to transition all of your weight, right? So this is a mechanism that we see all the time walking here on Earth. It's one of the key things. And so if you look at what they were talking about with the boot, if we have that rigid thermal plate, so here we can see my background's black. The rigid thermal plate is right here between our sole and the foot. When we go up onto our toes, our windlass mechanism is going to kick in. So we know that even in ski boots, like we just talked about, our hallux will dorsiflex. And so what you get is you get all of the ground reaction force that is actually going to be present right on your MTP joint there. And that's going to be one of the major issues. And so Becky and I, over the past year, 9 months, ever since we were at the conference this summer, we've been trying to prove that, yes, it does actually matter on the moon. So we don't know if that windlass mechanism is going to work on the moon, right? Or do we need it under lunar gravity? So we brought a bunch of people in. We tested them. We had them walk, jog, and run, or walk, run, and skip under lunar gravity. And we looked at what did their arch do? Did it raise? Yep. And we actually looked at the MTP joint to see if it actually was different, right? And everything. And so what we found was that the MTP joint does move a little bit differently, but we also found that the arch moves at nearly the same, right? So the arch still goes up, and our MTP joint does flex a little bit, but it's probably a product of weight. And so we have a little bit less MTP flexion. So what this shows is that the windlass mechanism works on Earth, and it is also going to be employed on the moon, which means that that rigid thermal plate probably is going to be an issue. And one other thing that we did find that was really interesting, we looked at contact time. So that what we saw with them on the moon, how long their feet are in contact, right? So we went through our people and we looked at how long their feet are in contact with the lunar surface, right? And what we found was that contact time is almost identical between the Earth and Moon. So that whole idea that people are just kind of lopping along the moon and hardly ever touching the ground, that's not what's really happening. What we found was that the contact time for lunar gravity is about the same between Earth and the moon. It's just they fly more. So if you look at the total cycle time here, that's why the moon here is way, way higher as far as time. The total cycle time is higher because they fly a little bit more, but they still are using the same mechanisms on the moon that we are here on Earth. And so that's really where our literature is right now, that we're showing, hey, this is going to be an issue. And before it becomes a health issue for the Artemis astronauts, maybe we need to look at it beforehand.
Right.
Yep. Isn't it also an issue of balance, right? Because you got to be careful, right?
And now I'm looking at that plate on the bottom, and I'm like, couldn't you put a joint on it there to make it a flexible at that joint
Who
point?
knows? I mean, I don't know. I don't know what's possible right now. No.
Right.
This is where, I mean, a lot of times we see where, engineers, they do a really good job, but sometimes when you put humans in the loop, engineers sometimes don't take the human into consideration, right? So I'm not saying that's what's going on here. I'm saying that that yes, a rigid thermal plate does mediate that issue, right?
Right.
But when you put the human in the loop now, it may actually cause other issues. And so a flexible thermal plate that may work. I don't know what that's going to do with the thermal properties of that rigid plate, right? So it may reduce the thermal properties of it. So there's issues there.
Yeah.
Right.
And I think that's one of the main things is that you never want to ignore like human testing.
Absolutely.
You want to be careful with humans. We're breakable, but we're very breakable, but you can't ignore that. You can't send something that's, no matter how many times you test it in the lab, you got to put it on a person first before you send it out into the ether, I guess, the world.
Yeah.
Now, is there any value of, let's say, strapping somebody in such a way that they're simulating 1/6 gravity as they walk, but walk in some type of soft material, you can like powder or something, and then take some kind of laser finder that measures the depth of the footprints at various places along the whole surface of contact to get an idea of how they're walking and whether it's as you'd expect given the design of the boot that you're using?
And with our Chandeska grant, we're actually doing a similar thing with that. So lunar regolith is a major issue, and not just with ours. So ours, you're absolutely right. When we're designing our outsoles, we actually try to reduce the amount of sinkage that the outsole will have into the lunar regolith. And the way we actually measure that is we have about 40 kilos of lunar regolith simulant in our lab. And so 4 different types. We have about 10 kilos of each. And we have a machine, we call it the Stomper. And essentially what you do is you take the outsole and you mount it to a boot. And then we have a counterweight on it that is about, it's about 70 kilos. 70 kilos is about what a human is going to weigh, 70 pounds, sorry, not 70 kilos.
Yeah.
70
Right.
pounds is what a human with a full portable life support system on the moon will probably weigh. And so what we do is we stomp it into the regolith, and we actually use motion capture. So I put a Vicon system on it, and we look at how fast it enters the regolith and how fast it slows down or how fast it decelerates, and then how far into the regolith it actually goes, right? And so we can actually test our outsoles in lunar regolith at 4 different types of regolith and get pretty good data off of that. But you're right, you don't want to be sinking into the regolith. It's going to be like running through sand if you don't.
Yeah.
The other part of regolith that I think a lot of people don't talk about is regolith is very, very tiny, and it's very, very sharp.
Sharp.
And so, oh, go ahead.
I was just going to comment that, regolith is more like shards of glass than it is sand. Maybe the same material, silicon dioxide, but the edges are much sharper because there's no weathering to round them off.
No weather. Yep. No weathering up there.
And once you actually know kind of what's going on with regolith, you kind of look at the old Apollo pictures a little differently. So, I believe Apollo 17, one of the astronauts is inside, and he's been out for a long time, and he actually has regolith on his face and on his hands. And you're looking at that, oh my goodness, that is not good.
Yeah, I guess there's a lot of problems with electrostatic.
Electrostatics as
dust
well,
will cling
yeah.
to you. It's like unwrapping a something that you get from Amazon or something, and that little piece of plastic won't get off your finger, right? Regardless of how you shake it. So that can be. I mean, that means everything's got to be externally sealed to the point where nothing can get inside to some moving mechanical device, because that could easily deteriorate that and cause that not to work after a while.
So an interesting thing that I noticed. So one of the things that we do is we do a bathing test, to see how much of the regolith the outsoles will retain if they actually step into the regolith and we pull it out.
So we literally bathe them. So we bury them in regolith and then we pull them out.
And so we had an electric scale we were putting the outsoles on to weigh them to see how much weight they gained by just being in the regolith, and it stopped working.
Yeah, it killed the scale.
It killed it.
The regolith killed the electric scale.
Wow.
So that's a really good example.
So we're gonna need to get a manual one.
And the other part is, the really scary part is that that regolith will eat through bearings in spacesuits, right? So, and that becomes, because even I can't remember, I think it was Apollo 12 where they were having issues with the suits after a few EVAs. So one of the suits was losing pressure during that time, and it was because regolith had actually started to eat away at some of the bearings.
Wow.
It's pretty crazy when you think about it.
Yeah.
Yeah, I know. I mean, when astronauts first went to the moon, or people have all these ideas to do all these different things futuristic, and one of them was to put like a very large telescope on the surface of the moon, and you could put it on the far side of the moon. You wouldn't have to worry about any interference with the Earth. But then people realize, how much dust is going to be on that mirror.
All the time.
Yeah, maybe we'll just leave it in space, rather than putting it actually on the surface of the moon.
Yep.
And I think that's probably one of the things one of the first things that I realized when I started working with different things like this, working with through NASA's, like that sort of thing, is that it's not just one thing. You get this one thing, and even if you solve that, or there would be the next thing, and then there's a, so okay, you can move your foot now, but now there's dirt and rocks, and then how are we going to get around the dirt and rocks? Then there's this, and then there's cold, and I don't envy. I mean, you look up and you're like, oh, the astronauts are so great, but I'd much rather be here looking up.
Well, you just wonder, what did I miss? By the time they go out. Right? Yes.
No, I've been sitting here thinking about that, what you said, that it eats through the regolith, it will eat through the bearings. And I've been thinking about that. Why would that work? And then I remembered silicon dioxide is quartz, and it has a higher hardness than steel. And that's why it does. It'll eat through these bearings because it's scratching them up to the point that it just chews through it.
Yep.
Yeah.
So.
And, like Wayne was saying, they are working. So essentially, you want to keep that dust out of your living environment, right, at all costs. Right. And because it's electrostatic, it's going to get into the computer systems. You definitely don't want that. So, it's all, from what I've seen with what Pablo does, essentially they're going to have docking systems where the suit basically stays outside all the time. The suit is essentially in kind of a mud area, and you dock it to wherever you're going. You get in and out of the suit, but the suit stays completely separate from your living environment to where it's completely sterile at that point. So they're figuring out a lot of these things.
Yeah, some is still going to get in, but that will mitigate it. There's still the seal that has to dock.
Yep. Well, I'm thinking like the lunar module, so you can imagine that, you go out, you do a spacewalk, you come back, and then you have to go to sleep, go the next day. That stuff is on your suit. You're bringing back in some rocks and soil and samples and stuff. And so you're going to breathe it. In fact, I think the Apollo astronauts made a comment that it smells almost like gunpowder.
Right.
The material from the moon. So that means it's getting into their throat, into their lungs. So very fine particles, that would do major damage, right, to your lung system if you took in too much of it.
It wouldn't be great.
Yeah.
Yeah.
It'd be about like asbestos. Which is needles. Yeah. And so I imagine the effect would be much
You're walking on the Sahara Desert in a windstorm.
Right.
So, this is a reason why Mars is actually going to be better than the moon. Because when you go to Mars, the particles have been weathered. So it's going to be different there.
Now, since you brought up Mars, so Mars has like 1/3 the gravity of Earth, where the moon is like 1/6 or something. So on Mars, how does that, where you have more gravity, right? The gravitational acceleration is larger. How does that affect the boot?
So with the boot, I mean, first of all, the temperatures are going to be different. So they're probably not going to have the thermal plate in there. So it's probably going to be closer to an Apollo boot where you're going to get MTP flexion or dorsiflexion. I will tell you this. We went to Sophie Orr. She was a graduate student not too long ago. We went to Johnson Space Center to use the Argos facility. Argos is a very, very high-tech offload facility. And we had done lunar gravity, Martian gravity, and Earth gravity. And she was just looking at asymmetries in gate. I will tell you that the movie The Martian, they actually got the gate pretty close. If you look at it compared to what we had our motion capture on. The boot probably is going to be close. I would say that eventually they've got to get to a fairly ergonomic design, right? So the boot now is kind of, their boots that they have are kind of rigid. Even without the rigid plate, they're rigid. They have to be moving towards an ergonomic design in those boots. And the reason I say that is, if you look at the moon, they're talking about 24 hours of UVA per week. You can't have people in an uncomfortable boot for that long. They have to be moving towards an ergonomic design. And if we go to Mars, it's going to be even more so, right? Because now you're actually putting pressure in the boot. You're probably not going to have the issues with the MTP joint that we're talking about, but you're still going to have some issues with asymmetry. We found some of that with the Martian gravity. So you've got some things that are going to be going on there. It's going to be a different thing, though. And it's just kind of a whole new ball game when you go to Mars.
I would imagine that once we get to going to Mars. Like, we've got to get to the moon first. And once we get to going to Mars, I'm assuming we're going to have a completely different suit.
Yeah.
Like it's going to you take what we've got now and it's going to be peanuts compared to what you're going to come up with when it comes to that.
The other thing that a lot of people don't realize is, and when I've talked to Dr. De Leon about this from a gate standpoint, from a kinesiology standpoint, I'm going to go back to the movie The Martian. If you look at their backpack, that's called a PLSS. It's Portable Life Support System. Theirs is very small in that movie, right? But on the moon, that is about 70 kilos. That's why I had that number earlier.
Yeah.
About 70 kilos in that backpack. And so you got batteries, you've got tanks, you've got everything in that. But the backpack, the PLSS, is actually about 6 inches aft, and then it's about a foot higher. So that's the center of mass for it. So it's actually going to bump your center of mass back and up. And from a gate standpoint, this causes major issues.
Yeah.
You're going to that's going to change all of your gate dynamics. And so when we go to Mars with the added gravity and a heavy PLSS, that probably is going to affect our gate. Now, they've talked about certain ways to go about that, reducing the size of it, but you've got physics at work here, right? You can only make a battery so small.
Yeah.
You can only compress gas so much. And so those backpacks, the PLSS is still going to be fairly big, and you're still going to have to make adaptations for that. And, humans, we like our center of mass right in the middle of our abdomen. When it gets moved outside of our abdomen to the back, and especially up and making us top heavy, we tend to fall over quite a bit. And so that's a major issue with all human gait.
Yeah.
So that's the tendency then would be leaning forward a lot. Is that how you
We would try to be leaning forward to compensate, which is also going to, because you're going to have a higher center of gravity too. So a higher center of gravity is going to make you top heavy. It's going to make you more susceptible to falling, right? So now you are pitched forward, you have a higher center of mass, and any obstacle that you're going over, you're now going to have to negotiate with a different strategy than you are here on Earth.
So you want to make your boots really heavy, so you're like a weeble. You wobble, but you
don't fall down. I was going to bring up something for our American audiences. 70 kilos, by the way, is roughly the average human. So
yes,
you're walking. So they're walking around.
Put your best buddy
on your back. There you go.
Yeah, put your best buddy on your back and try to walk around a little bit.
And we've done some modeling with that. We have some software where we can do forward dynamic simulations of gait, and we've put a PLSS on an astronaut, and we have them try to walk. And essentially, it's an iterative software program, so it'll try to figure out the best way to walk, and it does eventually figure out how to walk with the PLSS under lunar gravity. It does not do well under Earth gravity. It has major problems with that, but under lunar gravity, it will figure it out, and you're leaning forward, and it does have a propensity to fall over in those simulations.
And I know that there's some research going on currently about the best ways to prepare our astronauts for walking around up there. So, putting them in the spacesuit with it being really heavy and you're off balance, and then, offload, and then making them walk, stepping over holes and around rocks. And like some people are trying to use VR for that. Just different ways that if we can fix the problem here, or at least make you aware of what to expect when you're up there, the learning curve will be faster.
We actually have one of our graduate students is actually doing a VR thesis right now, actually in my lab under lunar gravity. So it's actually Keith Crispin's master's student. She's doing a project where she's actually doing a VR environment with terrain navigation under lunar gravity.
Yeah.
You could see, like, if you're on Mars or something, one way you could reduce the mass of the portable life support system would be just take shorter EVAs. Right?
Yeah, and that's what they're talking about. With the PLSS, I think they were talking about the PLSS generally has 8 hours of life support, and they're talking about just cutting it in half. And so you'd have a 4 hour life support, 4 hour life support time, but you would have half the weight at that point. You just have to come in and essentially recharge a little bit quicker.
Now, is there any considerations in the design and manufacturing of a boot that in case of a problem and something goes wrong, you don't want to be in a situation where, the some person X can no longer do a walk because their equipment has malfunctioned to the point where it's not useful anymore. But hey, we have instructions so we can 3D print a duplicate, a replacement copy. But you got to keep that boot using the right material that you can actually 3D print it, right? You can't have something elaborate that you can't do that.
Right.
And in case of emergency, of course, that would be important as well.
Yeah, one of our biomedical engineering students, Nick Bittner, he's a 3D printing expert, and he's been talking about how there's quite a bit of aluminum available on the moon. He was saying,
Yes.
"Oh, we can print aluminum. We can do aluminum printing from the in situ regolith." And well, okay, but essentially, they do quite a bit of different 3D printing materials. One of them is powdered metal. And of course, you don't want to take powdered metal into a spacecraft, right?
Yeah.
No.
So no powdered metal. But the other ones, powdered nylon, where you can do selective laser centering printing. You can do filament printing. All of these things are going to be really advantageous for an astronaut, right? I mean, if you break a piece of equipment or a piece of equipment wears out, we can just print a new one, right? And you're right, trying to make them as simple as possible to where they don't have to have a bunch of technical inputs that have to be done to get them printed is one of the main considerations there. And with our outsole, that's one of the things that we're trying to do is create something that you can print on the go. If it breaks, you can print another one right away.
Yeah.
Okay.
And of course, if you're on the moon, you're literally 4 days away from Earth.
Right.
Yeah,
Right.
you're out there.
So you can get resupplied if needed.
Yeah.
And see, that's one reason that we're really interested in this whole gate issue is because if the windlass mechanism not being able to be used in those boots is an issue and it causes a chronic injury, right? A chronic injury that maybe reduces your effectiveness. If you only have 4 people on your crew, and those are later missions where they'd have 4. Let's say you have 4 people on your crew. Each member of that crew has a mission critical task, right? And those mission critical tasks could be life-saving type tasks, right? And so if you're reducing the efficiency through an injury, a chronic injury that is foreseeable, that's an issue. And again, you're 4 days away, right? So it's not like you can just send away for a medic. You have to be able to be self-sustaining in situ right there as you're going. So if we can prevent chronic injuries from happening, that's one thing that you'd like to do. And the other thing is, are you guys familiar with what kinetic chain injuries are?
I'm not.
No.
A kinetic chain injury is so you have something that happens lower. So whenever we're walking around gate, all of our bones, all of our joints are very finely aligned, right? They are designed and they do very well walking, right? They do very well running. But everything stays in its own path. Everything has its own glide path. The joints work very well like that. But if you have an injury, for instance, at the ankle or at the foot, that may cause a misalignment at the ankle, which is then going to cause a misalignment at the knee and at the hip. It might even cause some spinal torsion that occurs. And so you have a kinetic chain where you get injuries that go up the extremities. And so that becomes a major issue where you could have chronic illness or chronic injuries that don't get better simply because we have these small injuries that now become a major medical problem later on.
In other words,
I don't know.
In other words, the hip bone's connected to the leg.
Exactly.
Right.
And if you have any age on you whatsoever, if you ever wake up and your knee hurts and so you're kind of limping around that day, eventually you're like, why does my shoulder hurt now?
Yeah.
Like it's because you've been walking
And again, when you have a crew of 4 people, it's not like you can just take a day off. There are mission critical tasks that everybody has to do on a daily basis. So these injuries won't go away.
Now I'm thinking in terms of, would you cycle, the door type stuff would you cycle so that only 2 at a time were actually going out, so that the feet and other body parts could rest for 2 of them, and you cycle through the crew like that.
The big thing that we would like to say that, the rigid thermal plate, right?
Mhm.
I think that's an excellent idea. And I think that probably is the best solution for the thermal issues that we have. However, there probably are other mechanisms that we can employ in the foot with the rigid thermal plate to activate that windlass mechanism appropriately.
Right.
So we're not saying that the rigid thermal plate is a bad idea. We're saying that it needs to be pushed a little bit further, and maybe some more technology needs to be implemented into that boot to actually allow the natural mechanisms to occur.
That's neat.
I'm thinking about like in the far future now, if you go to other environments like the moons of Jupiter, we're going out hundreds of years into the future. So by then have lots of development in material science, right? So we could possibly have something
Right.
that with a lot greater flexibility or give to it, and yet still provide the thermal properties that we need, right? In whatever environment we're at. And of course, we'll just use AI and everything, right?
Right.
So-
Well, I'm thinking due to the radiation environment in a place like that we probably just end up doing like the diving bells, where you've got electronic elmos that you activate.
Yeah.
Or you could just have a shoe closet in the space station, and the gray ones are for like moon, and
Yeah,
the red ones are for the Mars.
you almost like wonder, why do we even have like space boots if you're just on the International Space Station? Because do you really need it, right? Because you're not walking, right? You're just floating, like your
Floating
spacesuit's a spaceship, right? You're just floating inside of it.
Yeah.
And the
would say
answer
that-
is occasionally you've got to go outside of it, and then you need the boot because of
But
the environmental
inside you just need
concerns.
dippy socks.
Right.
I would say that the space stations, the ISS spacesuits currently, the ones that we were using with the space shuttle, they're not probably as ergonomically designed as we would like. You probably are not going to want to walk around in that spacesuit.
Nope.
Right.
Yeah, I was like, and even if you were to like when you're doing a spacewalk on the outside of the space station, you can put different like handholds and footholds and all these things.
Yeah.
It makes sense that you would design some type of a boot that has like a hook on the end, like an elf or something, right?
Yeah.
Now you could more easily attach and get better grip so that you don't move around when you're turning a bolt, torquing something, right? So you can make sure you don't spin with it.
That's a good idea.
That actually brings up something really interesting about the ISS astronauts. A lot of times you realize the bottom of their feet, so where you have that nice pad, on Earth, that pad is good, right? We want that pad of tissue to be able to cushion us when we're walking. Often that bottom will slough off. So if you're up there for long enough, that bottom callus layer will slough off, right? So you'll just have kind of baby feet, right? Well, you don't need it at that point. You will when you get it back. However, you do start developing what they call alligator feet. And so you get a thick callus layer actually on top of the MTP joint.
Yeah,
and
because that's how they're gripping stuff. They're sliding.
Because they're always
yes.
gripping with that foot on that way. So your foot actually adapts to that environment. And that's what's really interesting about the human body, how well it adapts to certain things. It's just kind of really crazy.
And the one thing is that the human body does a really good job at adapting. Unfortunately, that beginning phase of the adaptation a lot of times causes some form of injury.
Yeah.
Until you either change the way you're doing it or you just get used to it.
Yeah.
And
I've watched experiments on shows with that where they have a bicycle with the gear on the under the handlebars, where the tire actually turns the opposite way to where you turn the steering wheel. And people eventually, after a lot of work, figure out how to ride that bicycle. But then when they go back to a normal bicycle, their body still wants to do the old way.
And what's really funny about those, when they do that, the children pick it up really, really quick.
Yep.
But adults, they have the hardest time with that bike.
I actually know the term for that. That's neuroplasticity, and we
There you
lose
go.
it as we get older.
How do you spell that, Robert?
Yep.
Don't ask me that one. I know the term.
Well, it's kind of related to like if you want to learn a second language, learn it as a young child. It's much
Right.
easier to try to learn it
Yes.
as an adult.
Much
Right.
It's
easier.
awful.
Yeah, but I was thinking, you know, if you're on the space station for like a year, and we've done that, several people have done that sort of type of mission.
Mhm.
When you come back to Earth, are your feet so sore that you got to have different, you know, like different shoes, like custom-made shoes to protect
don't-
them?
I don't know. I'm assuming you would. I would assume that within your shoes, you're going to have enough padding that it's probably not going to be an issue. It's going to be when you're walking around barefoot at that point,
Yeah.
until you build up
The
the
calluses
plantar
again.
callus
Yes.
that you get. Good. You know, one of the interesting things is that inertia. They don't quite when astronauts do come back after that long, they have a hard time taking corners. So when we walk around corners, we kind of understand how inertia is going. We can kind of navigate a corner. A lot of times when the astronauts first come back, they'll kind of drift off when they go around a corner.
Interesting.
So-
That's neat. That's cool. I had never thought about that, but yeah, when you've got gravity and tactile
Yep.
information, you don't tend to drift.
Yeah.
And that's another reason why it's so important, you know, to teach the astronauts how to move around up there, because that is the learning curve that you're expecting to be able to walk the way you do when you're on Earth, and then we put you somewhere else. That ain't how it's going to work.
Right.
And it's the same way as when we put them underwater. You
Yeah.
know, we put them underwater and they go around and learn how to be weightless and everything. Well, now we've got to teach them how to not necessarily be weightless, but just less.
Right.
Wait, less.
Wait, less.
So that introduced the question: is there certain types of exercise that you can do on the space station to maintain the strength in your feet?
That's interesting. So, you know, currently on the space station, they do quite a bit of workout. They do rows and stationary bike. They do a
Mhm.
few of those things, right, to keep the major muscle groups strengthened. And they do a reasonable job of staving off wasting away or atrophy of the muscles. Bones actually are a bigger issue because you need weight bearing exercise to maintain bone. It would be interesting to do exercises for the feet to keep that plantar fascia from loosening up. That may actually be an interesting thing. I know that what's interesting about weight equipment on the ISS or weight equipment on any of the spacecraft. We just did something with para astronauts at Johnson's where we were in the Orion capsule, and they have a little box, and it's just called the box. It's a weight. It's an exercise piece of equipment. Basically, it's a rowing device, right? So they like to save a lot of space. So if we could work in some type of exercise with the existing equipment that they have, I think that could definitely be something they might do.
Interesting.
I think we should work with ballerinas.
Ballerinas, there you
Yeah.
go. So
I'm telling you, that if you're looking at like ankle strength and foot strength,
ballerinas are
talk
pretty
to a
good.
ballerina, because I guarantee they've got some pointers for
Of
us.
course, their toe health isn't very good.
They're, well, you know, give and take.
Yeah, you could even think of like ice skaters, like hockey players, and their
Yes.
Yeah.
Mhm.
Yeah.
because the foot is
And-
so restricted, right?
Yeah,
Yep.
absolutely.
And then essentially what we get into in kinesiology when we talk about that is, well, the big word is specificity, but you've got like sport specific exercises. So if you are in hockey, there are some exercises that we might have a baseball player do that we would never have a hockey player do because they never have to do anything like that.
Right.
Right.
However, there are probably some very similar ones, like the exercises we might take them through in order to strengthen their swing, their bat swing. We might take hockey players through a similar one for their stick swing. So
Yeah.
There could be something similar with gait and astronauts as well. So
Yeah, so-
specificity would be something that we could actually look
Right.
into.
I'm thinking like if you made the skate not like it is now, but make it more flexible in the right area, that would give more power from the legs transmitted to the contact of the skate on the ice. That would make you a better hockey player in some sense.
yeah,
The one thing I do know about sports is they like to invest in being good. So if that was
Yeah.
If there was an advantage in a flexible skate, I am certain that somebody has looked into it. It's one of those things that professional teams, they will invest in biomechanics studies to determine the best way to get absolute performance.
And they do. Okay.
Yes.
Never
Yes.
doubt. They are still trying to find out what exactly is the best. So
Absolutely.
Yeah, you could
Yeah,
like
it's true.
you could patent a skate and make a fortune, right?
right.
If you gave you like 5% more power or something compared to
I'm
somebody.
sure.
And,
Absolutely.
5%. If
Yeah.
you're looking, and that's the one thing when you look at Olympic sports, that's something we talk about all the time, that 5% would be massive. When you're talking about professional or Olympic, 1% is something thereafter, right? Because at that level, everybody is so good that, it's just the day and the time that kind of separates people. And if you can give them a 1% advantage, that's worth
huge.
whatever you can invest in.
The same thing in NASCAR, actually, because I know that I remember this story about somebody, their pit crew left off their oil cap and they were disqualified because all the cars are that tuned that just a little bit less weight and you're potentially getting an unfair advantage.
Yeah, so if you wake up some morning before the big competition in Olympics, then if you had an upset tummy, that's enough to drive you from getting a gold medal to getting no medals, right?
Right.
Absolutely.
And that's how they talk about getting into like a mind game, because it could come all the way down to do you feel confident this morning?
Sports psychology, that's all they talk about.
That's it. That's it.
Yeah.
Wow.
I could see him like use anger some way, right? Or some way of getting adrenaline going, right? To get you, this is the guy you lost to the last time, right? You lost your medal.
I like that. Positive affirmations for astronauts. I like that.
There you go. There you go.
If you don't do well, you're going to get replaced by somebody else.
Well, if they can fly, then they're fast enough.
Right.
Yeah.
4 days from the moon and a year from the Mars.
You wake up every morning and say, I am out of this world.
How many days do I got to wait for the planets to align again?
Yeah, exactly.
There you go.
But anyways, I guess we could time to wrap it up. And thank you very much,
Thank
Becky
you.
and
Yeah,
Jesse, for
thanks.
doing this.
And
Thank you so much for allowing us to come and talk about our research.
absolutely.
We love talking about it. And
Yeah,
not a lot
I know.
of people
I've
know
never
us.
known a researcher that didn't.
Right, I know I learned a lot.
Exactly.
So very, very interesting.
I love to nerd out.
Yeah, very much.
Now, if you would like to learn more about what Jesse and Becky do, then come to the University of North Dakota, and you can be major in the Department of Education, Health, Behavioral Studies, and so on and so forth, or anything else that goes on campus. We welcome you both on campus courses and also online. There's a lot of things that people can take. Our next podcast will be next Tuesday on February the 18th, and we always leave you with a quote at the end.
Always.
And I try to make it relevant to the discussion that I'm going to have, because I have to do this ahead of time, right?
Right.
So here we go. It's a quote from a singer. His name is Paul Brent.
Okay.
And here's the quote. Don't tell me the sky's the limit when there are footprints on the moon.
I like it. That's a good
There you
one.
go.
Tell me this-
Thank you once again for joining us, and thank you for watching.
Thank you, folks. See you next week.